All right, I thought I'd do a lecture to do a quick review of the material that we've been talking about that's going to appear on the next exam. These are the topics, and I'll talk briefly about each one. And if you have more questions about them, you can see me or look at some of the other videos that are already posted. One of the topics is the three-block problem, which, as you know, involves three blocks of different masses and a force acting on one of the blocks from one of the sides that will cause the blocks to all accelerate in a given direction. And that acceleration is a function of the masses of the blocks. And the acceleration is going to be the force divided by the mass of all the blocks together. See if you can see that. And then once you know the acceleration of each of these blocks, you can determine what forces are going to be the interaction forces between the blocks. If this is block 1, this is block 2, and this is block 3, you have the interaction forces F12, which is the force of block 1 acting on block 2, which has to be equal to an opposite direction of F21, and F23, which has to be equal and opposite direction of F32. And the nomenclature here means that F12 means the force of block 1 acting on block 2, and F21 means the force of block 2 acting on block 1, etc. for this too. Okay, so we know that, and we also know that if I draw an individual block here, call this block M1, that if it has a force acting on it, it's going to have the force F21 acting on it from this direction. And so the net force acting on block M1 is going to be F minus F21. That's the net force acting on block 1. And of course, in all the examples that we had, those were given numbers. And I didn't put any numbers in here. But that net force acting on block 1 has to be such that it will result in the acceleration of block 1, which we've already calculated. And then we can follow with blocks 2 and blocks 3. We did quite a few examples of the three-block problem that was on the homework, but that is one thing you can expect to see on this exam. And again, the exam is going to be 20 multiple choice questions. It will open 10 o'clock Wednesday, and you have till Sunday night at midnight to take it. Give yourself 90 minutes unless you have special accommodations. Another set of problems that we looked at quite a bit were the elevator problems. And these involve somebody standing in an elevator on a scale where the elevator is either accelerating upward or accelerating downward. And we applied Newton's laws to this. Remember Newton's law, Newton's second law, F net equals ma. That is going to be something we'll apply in this case, and in pretty much any of the cases we've been talking about, F net equals ma. So for the elevator problem, Fn on the person is going to be an upward force, and Fg is a downward force. So that's what F net is equal to. And that difference is equal to ma. And so that's how we approach this problem. Again, when we're looking for the equivalent weight, we're looking to solve for Fn. So we'd say that the normal force is equal to the weight of the person plus ma. And if A is positive, of course, the apparent weight will be greater, and if A is negative, it'll be less. That's a brief review of the elevator problem. Get this in place so you can see it. think you can see that. Apologize. This is comedy of trying new and different things to get the videos going so that you can see them well each time. All right. The other things we spent a lot of time talking about were free fall kinematics. Can you graph position, velocity, and acceleration in a free fall problem, whether the object is thrown upwards or downwards from some height? And can you do the necessary calculations to determine when the object will hit, how fast it'll be moving when it hits, or that's to say its final velocity. So we did problems involving free fall kinematics, quite a few of those. Check the examples if you would like more practice with that. There's the jumping problem. So for the jumping problem, the question, of course, is when a person leaves the ground, how fast do they have to be moving to get to a certain height? That's the jumping problem. Of course, the landing problem is if they start from a certain height, how fast are they going to be moving right before they hit the ground? And then the question, of course, is how do they get from the crouched position to, excuse me, to the initial velocity of the jump. Over some small distance, there's an acceleration that takes place that leads them to have the initial velocity that leads them to get to the height that they are trying to reach. So that acceleration is determined using not the free fall kinematics equations, but the kinematics equations that rely upon the person being on the ground and having an acceleration other than that of g. And the same is true about the landing problem. When they're landing, they also have the acceleration associated with coming to a stop, with starting with their legs straight and ending up with their legs bent as they're crouching after their stop to keep their knees from breaking. All right, so the equation that was very useful for these cases was the equation, you remember, v final squared equals v initial squared plus 2a times y final minus y initial. That kinematics equation was one we applied quite a bit. All right, so that was the jumping and landing problem. The other thing that we can also apply to that is, and you saw some of this in some of the homework problems, is looking at the forces associated with somebody who's, let's say, in free fall. So if somebody's just in free fall, say they jump out of a plane, here's the plane, I'm going to ignore air resistance. As soon as they jump out, the only force acting on them is going to be the force due to gravity, and they're going to be accelerating downward. When they land, of course, hopefully the parachute will open and all that, but when they land, even from a jump, let's say, there's going to be a very big upward force. That's the normal force. It's going to be quite big, but Fg is still whatever it was when they jumped out of the plane, same size. And that's as they're landing. Then, of course, once they've landed, this is as landing, once they've landed, then all the forces have to balance out perfectly so that they'd have Fn upward, Fg downward, where Fn equals Fg. So that's applying free body diagrams, which is the last item on this list here, to these cases of people jumping and people landing. Force and acceleration, how are those related? This goes with Newton's second law, that you could say F net equals ma. So if you have a graph of force versus time, graph of acceleration versus, this is the net force, let's say. Graph of acceleration versus time is going to have the same shape. The difference being that whatever the value of force was here, the acceleration would be that force divided by the mass at any time. That's the corresponding value of what the acceleration would be if this were acceleration versus time. All right. Newton's laws. This is Newton's second law. This is the one we used quite a bit. Newton's first law is a simple case of that. That's where acceleration is 0, and so the net force is 0. The object just continues with whatever motion it had, whether it was stationary or moving with some direction and speed. And Newton's third law is the law of action-reaction, the tug of war, where both forces on both sides of the rope are going to be the same. That would be Newton's third law. So those are Newton's laws as we talked about them. And then one of the last things we talked about was friction. Friction, of course, there's two kinds. There's static friction and there's kinetic friction. Static friction has that equation, and kinetic friction is this one. And friction is really just another force. So if there's an object here that's experiencing friction, it has to be experiencing some other force in order to experience friction. If it's static friction, friction can't exist. Static friction can't exist by itself. There has to be somebody pushing on it, and then the static friction will try to oppose that until you push hard enough to get the object to start moving. But you can write friction as another force. It's just that when you're calculating it, you can use this equation. You have an additional special equation to use for cases where you have friction. So that is what's unique about friction. And so what can you do with friction? Well, one of the things you can consider is, let's say you have an object here, and it's moving with some constant velocity. Some constant velocity of whatever, 2 meters per second, 3 meters per second, it doesn't matter. And that you're pushing on it to maintain that motion. That means that there actually has to be a kinetic friction force that's opposing your pushing force, and the two have to be equal because acceleration equals 0. And if acceleration is equal to 0, there's no net force acting on the object. So if there's no net force, the acceleration is 0, and it'll be moving at a constant velocity. So you could figure out what the friction force is based on how hard you're having to push the object. And once you know the friction force, you could calculate the coefficient of kinetic friction by knowing the normal force. You know the normal force because if you know the mass of the object, you know that there's a force due to gravity that's pulling the object down, that there's a normal force that's pushing the object up. So you calculate that normal force, multiply it by the coefficient of kinetic friction, get the kinetic friction, but you're solving for this because you know the kinetic friction has to be equal to the force at which you're pushing the object. That allows you to calculate the kinetic coefficient of friction, which is something you did in lab just a few days ago. That's as far as the exam will go. There will not be any problems on it regarding vectors, which we'll talk a little bit about today, nor will there be problems on it about the Atwood machine or the block on the hanging block problem that we also talked about in the last lecture. Okay, if you have questions, of course, you can email me, and I will talk about vectors in the next video.